So in the last lecture we have discussed about different types of modeling. So let's begin further examples. Okay, so I am going to give you people the examples of distributed models and other models. Okay, so let's begin. So consider a fin. Fin is nothing but the extended surface. Okay, so this is, suppose this is the extended surface, and this extended surface is attached to some some solid plate which is at temperature T0, right? T0 temperature. Now this fin will have the temperature profile Tx along this direction, x direction, right? So take a small strip like this. So heat going in is QA at x location, and heat going out is QA at x plus delta x, and some heat will be going outside the atmosphere, okay, outside this fin to the atmosphere. So that's Sp delta x. H is the heat transfer coefficient, P is the perimeter. Okay, so that is related to H P delta x, and T minus T infinity, surrounding temperature is T infinity. So we can write the cell balance. So accumulation we consider at first steady state. So accumulation term will be 0, and then in heat in Q subscript A at x minus QA x plus delta x minus the heat going outside from the fin surface to the atmosphere, that is minus Sp delta x T minus T infinity. Now this will settle into d dx of Ka dt or dx minus Sp T minus T infinity is equal to 0. Now if Ka is both constant, K and A you can take outside, then d2 T over dx square. So this is nothing but the second order ordinary differential equation. Is it linear or non-linear? This is linear. Okay, now this is second order ordinary differential equation. So we need two boundary conditions. So second two boundary condition, one is at the base of the fin, that is at x is equal to 0. X we are taking in this direction, so at x is equal to 0, t is equal to t0. Okay, and at the tip of the fin there could be a boundary condition, two types of boundary condition, means at x is equal to L, t is equal to t infinity, means this tip temperature of the fin could be equal to the ambient temperature T infinity, or tip could be so thin that the flux of energy that is going out from the tip is 0. So dt over dx at x is equal to L is 0. Okay, so this is linear, provided, why is it is linear? Because t is the unknown. Okay, and k is constant. Even if a is the function of x, but a is the function of x, x is the independent variable, so independent variable could come right here. Okay, so this will not make it non-linear. Now what will make it linear? If some function of dependent variable will come along with the dt or dx. So k, if thermal conductivity will become the function of temperature, which happens in case of many materials. So k will be the function of t and dt or dx. So as a product this will appear, then it will become, this equation will become non-linear. Okay, so how to calculate the heat dissipated through this fin? Okay, so you can calculate it in two ways. Okay, minus, once you will get, after solving this differential equation, you will be getting what? You will be getting after solving this differential equation, you will be getting, after solving this differential equation, you will be getting t as a function of x. All right, t as a function of x. Okay, once you have the t as a function of f, you can calculate how much heat will dissipate. So you can calculate it in two ways. First way, what is the heat that is going into the fin, means minus k dt or dx at x is equal to 0 multiplied by a is equal to r, or the second way is the heat that is going out through this fin surface to the uh, ambient or atmosphere, right? So you can calculate this 0 to L, you have to integrate sp tx, t is the function of x, minus t infinity dx. Now you see, once you have the profile of dt, temperature as a function of x, you have to integrate, or you have to take the derivative. So we need numerical differentiation and numerical integration techniques. Okay, and another situation that we are taking now, we will relax the assumption of steady state and we will take the transient situation. Now in the case of transient situation, the left hand side will not be 0, like in this equation left hand side would not be 0. So this would be del rho a cpt over del t is equal to del x, rest will be the same, del x k del t or del x minus sp t minus t infinity. Now this is partial differential equation. So you know, this is distributed model and this is also dynamic model. Distributed, why? Because it depends on x, temperature depends on x, right? And dynamic because this unsteady state term is not 0. So you will need initial condition also along with these boundary condition, two boundary condition. So initial condition, let's say tx at any x, initially the fin temperature is at the base temperature, right, t naught. So what we saw that this differential equation we got, partial differential equation will we got. Okay, we got set of linear algebraic equation. So after all this, if you numerically solve this equation, this will also be converted into set of algebraic equation. When you discretize any PD's, partial differential equation, or any other, you know, uh, linear differential equation as well, you will, once you will discretize partial differential equation by any method, finite difference method or finite volume method or finite element method, you will get the set of linear equations. If you even get set of non-linear algebraic equation, you will try to convert it into set of linear equations. So we must understand how to solve them. So we need to discuss in that regard some basic concepts of linear algebra that must be used in this mathematical modeling. So this is the some review of the concepts related to linear algebra. Now consider this dx1 dt is equal to a11 x1 plus a12 x2, that's the linear part, plus phi f1 x1 x2, that's the non-linear part. Next equation is dx2 over dt is equal to a21 x1 plus a22 x2 plus phi f2 x1 x2. So this is the linear part, okay, and this is the non-linear part. Now if phi tends to 0, then this will become the set of linear differential equation. We can write it in vector form x. So dx vector over dt is equal to a matrix part, this is a11 a12 a21 a22 and x vector plus phi f. Okay, so if phi tending to 0, this is linear, and if phi is small, then it is mild non-linear system, and if it is large, then system could be non-linear. Okay, so you know, often in the problems you have to solve, okay, for dynamic system and stabilities of the solution, you have to discuss with related to any problem. Now you can draw the graph also. So for let's say n is equal to 2, let me write this one. Okay, So this is let's say pi. So if you draw curve, so this is any degree of non-linearity you can handle for n is equal to 2. Now if n is equal to n is greater than 2, then you have to use certainly numerical tools. If n is equal to 2 or less than 2, you can handle any degree of non-linearity, means some analytical methods are available, but greater than 2 there is no analytical method, you have to go for numerical tools, numerical method. Okay, now as you know that any for lumped steady state you will get the linear equations. So this will be the building block of numerical solution, linear equations. So we will review some concepts of linear algebra. So linear algebra we will review. So this is matrix matrix we will review some concepts related to matrix. Okay, so Gibbs notation is a is equal to aij, a is equal to aij, where I might go to 1 to m and j might go to 1 to n, right? So this is the row vector x vector that could be represented by xi, x1, x2, x3, xn. All right, now it could be column vector, right? Like y is equal to yj, y1, y2, y3, ym, right? So the elements can be real or complex. So MATLAB can handle these row vector and column vectors and matrices very easily through tools. Okay, so MATLAB naturally handles these and also deals with the operations on these rows, columns, as well as matrices. So let's see what are those operations, right? So those operations, it could be addition, like if you have two matrix A and B, then you can add these two matrices to get the matrix C. And rule is, what is the algorithm to add this? Element by element addition. So we have represented this Cij is equal to Aij plus Bij. So we have written in index form to tell about the algorithm, right? Now this matrix addition or subtraction, matrix addition is commutative because A plus B is equal to B plus A, and it is associative, means A plus B plus C is equal to A plus B plus C is equal to A plus B plus C, means if you add A plus B then add C into it, or if you add B plus B and C and then add A into it, both are same. So this holds associative law and commutative law, as well as scalar multiplication also work. So if K is a scalar and you multiply the A matrix by this scalar, you will get the B matrix, and the algorithm is multiply by this scalar K to every element of matrix A. So Kaij is equal to Bij. So this is the whatever index notation form we have written, this is the actual implementation. So you have to write the code for this, okay, and you have to put a loop around each indices like I and j, right? And next, so this is about addition and subtraction. Now next operation is about multiplication. So this holds like scalar numbers, 2 plus 3 is equal to 3 plus 2. Okay, so commutative and associative also with the scalars, what you will find with matrix. So you can compare and you can get the same same laws followed, like commutative and associative for both for scalars as well as for matrices. Now as far as multiplication is concerned, here there will be a problem. A C is equal to A V, but this is not something element by element you can multiply, but it follows the rule Cij is equal to sigma k is equal to 1 to m a I k b k j for each I j, means k is the repeated index here, so you have to sum over that index. Okay, so it will be mm, it will contain all the range of the values of the k. Okay, so what is the algorithm? That product of row with a column, element by element, and then add them up, sigma. Okay, so how you can interpret? So aik means if you fix I and change k, because k is the repeated index, so sum over that, change k. That means if you you have fixed I, means ith row, and ith fix I means ith, and change k is the column. So change, you are going through ith row and kth column, or you are changing throughout all the columns. That means you are considering one row, that is ith row. So if you fix I and change k, you will get the ith row. Similarly, if you fix k, if you change k is the repeated index, and fix j, you will get the column j. So it is like you are multiplying ith row with jth column, element by element, and sigma represent for add them up. Okay, so this is the multiplication rule that I have explained. Now this AV follow the commutative. AV is equal to BA. It is not always possible. Okay, so this AV, and this is not element by element. If you want to multiply element by two matrix, then there is a MATLAB algorithm, that is A dot star V. This is element by element multiplication in MATLAB. Okay, so if you want to multiply in MATLAB, so how will you implement that? So A star V. So suppose A is a 4 5 6 first row, second row 1 2 3, and B is 1 3 2 2 3 1. So in MATLAB, what will you do? In MATLAB, they will be defined as follows: 4 5 6 and semicolon will separate the other row. Then you will bring the second row, that is 1 2 3. Okay, so this defines 2 cross 3 matrix A, and semicolon separates rows, right? Now similarly you can define B matrix, this one. So 1 3, that is first row, semicolon second row 2 2, then semicolon 3 1. Okay, now you will put A star V, that will be stored in C. So this will calculate the product, and that will result into 32 14 28 10. So this is the MATLAB implementation. Now we are talking about product. So we have talked about C is equal to AV, and in MATLAB implementation you will write A star B, right? And suppose and second is, this is one type of multiplication, and second is called Hadamard multiplication. That is sur product. So that is element by element. So for this A and B both matrix must have same dimension. Here you will have this suppose M cross n, this is M cross n matrix, then this must be n cross something, means the second index of this A matrix must be the first dimension of must be equal to the first dimension of this B matrix. But for this they must have same dimension, because you are going to multiply element by element, Hadamard product. So this gives Cij is equal to Aij Bij for each Ij. So in MATLAB implement, if you want to implement, what you will do? See, this is 4 5 6 1 2 3. So if we take transpose, means rows into column and column into rows, then it will be 4 5 6 1 2 3. So this both will become of the same dimension, that is 2 cross 3, and this will be 2 cross 3. So we are going to multiply those. So we transpose it, we take transpose A transpose and dot star. dot star for element by element multiplication. So AT dot star B, this will give us C is equal to 4 3 10 4 18 3. Now next product is, so this one, this is the one type of product that is not element by element, and this is another type of product that is element by element, and another product is Kronecker product, and it is represented by cross in the circle A cross B, and it is like, you know, you have the matrix B, then you will multiply each element of A11, A12, A1m, each element of A with V, and you will get this C. Now we want to define also the identity matrix that is having diagonal element 1 1 and rest of the elements are 0. So you can represent in the index notation delta I is equal to 1 if I is equal to j, means diagonal, for diagonal, and non-diagonal element I means I does not equal to j, this is 0. So you will get this in index notation delta I. Now why we define this I? Just to define, to get the notion of inverse matrix, means division concept, very similar to the concept of division for scalars. In the matrix also there is a concept of division, but we can define it through identity matrix. Now, right, so identity matrix is AI is equal to A. Just like if you multiply 3 or 4 or any numbers by 1, you will get the same number. So if you multiply any number by 1, you will get the same number. So you are multiplying by 1, so 1 is the multiplicative identity. Similarly, I is the multiplicative identity for a matrix A. So this is the, you know, scalar counterpart I have explained, like x dot 1 is equal to x, and so in place of 1 there is I. Now if AB is equal to I, then B is equal to A inverse. So any matrix, suppose you want to get the inverse of matrix A, so inverse of the matrix is defined as, like, if you multiply that matrix, that inverse matrix, with the matrix A itself, suppose you want to get the inverse matrix of A, so you must have such a matrix, you will have to find such a matrix that will be multiplied with A, will give you the identity matrix. So this is similar to that. Suppose 4 you are multiplying by x is equal to 1, so x is equal to 4 inverse. So this is the scalar counterpart. Okay, so this is very similar to division. Okay, you can understand, you can think of like that. So how do we get the inverse in most efficient way? Because the question is, what is inverse? You know, AB is equal to I, then B is equal to A inverse. This is the definition, conceptual definition. Now what is the computational easy way of understanding? Means efficiency of operation. So we must get the inverse with the least number of arithmetic operation. Okay, so inverse, to get the inverse we must have least number of arithmetic operation. That for that purpose you have to develop some efficiency scheme. So why efficiency is important? Because if you discretize the PDs, then you will get the millions of equations, and so you will get the millions by millions matrix, and inverting it in by direct method is a big challenge. Okay, so you must understand some methodology. Okay, so methodology, computational ways, so that we get the inverse with the least number of arithmetic operations. Next concept in this sequence we must understand, that is the power of matrix. A square is equal to A multiplied by A cube is A multiplied by A multiplied by A, that is A square A or A square. Power law also follows like scalars. A key power P, A key power Q is equal to A key power P plus Q for positive integers PQ. So having extended the definition of powers, we can extend this definition to exponential from scalars to square matrices as follows. For scalars, you know, exponential number for scalar alpha, A e to power alpha 1 plus alpha square by 2, summation notation you could write like this. Now for matrix, square matrix A, the exponential matrix is e to power A. It will follow, but in place of 1 you will have the identity matrix. Rest is just you replace alpha by A. So A I plus A plus a square by 2 plus dot dot dot. In index notation this will be like this. Now one operation, so this is all scalar counterpart. Okay, so whatever operation we have studied till now, these have scalar counterpart, but one operation that does not have scalar counterpart is the transpose of a matrix, that doesn't have direct scalar counterpart. Okay, so it is defined as the exchanging rows and columns of the matrix, means you will change the indices, switching the indices. Vij is equal to Aij, Vij is equal to Aj I, means you are switching the index. So B is equal to A transpose. Now for addition, A plus B transpose would be equal to A transpose plus B transpose. This is easy to verify, but what difficult to verify, not is so easy to verify, but it is true, is the product transpose of the product A B transpose, that is not A transpose B transpose, but in the reverse order, like B transpose A transpose. So this is about all about the matrix some operations. Now some matrices will have the special structures, like diagonal matrix, only diagonal, non-zero elements only along the diagonal. Okay, and rest are zero. And lower triangular matrix may in lower triangular matrix, non-zero elements on or below the diagonal. Non-zero elements you will get on or below the diagonal, and rest will be zero. Similarly for upper triangular matrix, non-zero elements would be on or above the diagonal, and rest are zero. Okay, so why do we need the definition of diagonal matrix, roll triangular, upper triangular? Just because if you follow the Gauss elimination, then it will be having two steps, forward elimination and backward substitution. So you will and LU decompositions, so diagonal matrix you can represent D, lower triangular L, and upper triangular U. Now this LU decomposition essentially capture the Gaussian elimination, that is that consists of two steps, forward elimination and backward substitutions. Now other special type of matrix is tridiagonal matrix. It is represented by T generally. This has non-zero element on the diagonal, so this is the diagonal this is diagonal elements, that is non-zero, and one off diagonal row, means one above on each side, one above and one below. These are non-zero and rest are zero. So these are called tridiagonal matrix. Now what is its importance? Because when we develop Gaussian elimination, we will recognize that when you have a special structures like this tridiagonal matrix, we can tweak the Gaussian elimination scheme to stop eliminating all things that are already eliminated. It is like zero, that is zero. So why we spend time multiplying 0 by 0? Okay, so won't use the regular inversion method like Gaussian elimination. So switch from Gaussian elimination at that moment to Thomas algorithm. Okay, so recognition of these matrices are very important, and some matrices you will get, and it is very frequent, means it is very common to get the tridiagonal matrix, because if you are discretizing partial differential equation, then at every grid points you will find the solution to the next grid point will depend on the previous grid points. Similarly, if you are solving different stages problem, mass transfer operation or any other thing, then the result of outcome of the first stage will affect the outcome of the second stage. So you will get the tridiagonal type matrices, or some matrices that have a block diagonal structure like this. Okay, means you will get some blocks like this, and you will have tridiagonal within that block, means these the three diagonal rows will be non-zero and others will be zero. Okay, so block diagonal matrix. Next, in the next lecture we will discuss about determinants, and we will go more deeper into the linear algebra fundamentals for introduction to mathematical modeling for chemical engineers. Thank you.